Assalamu alaikum. Welcome to the online class. Today's chapter is amplitude modulations and demodulation, and the course title is EEE 351/352 Analog Principles of Communication Systems. Here I am Dr. Ishan Kaleem from Kamsar University, Islamabad, WA campus. Let's begin the lecture. These are some lecture contents which we will cover in this video. First of all, we will cover what is vestigial sideband modulation and why we need this modulation. What is the importance of this modulation? Because there are a number of modulation schemes which we already studied in the previous lectures that exist. So why we need the vestigial sideband modulation? And in the later section of this online class, we will cover the VSB demodulation as well. Okay, let's move on. Vestigial sideband modulation. So, vestigial sideband modulation is actually the compromise between the double sideband and the single sideband, but at the reasonable increase in cost. So, what does it mean? It means that in double sideband we transmit two sidebands, right? One is the upper sideband, the other is the lower sideband. In the single sideband, we only transmit either the upper sideband or the lower sideband. So, whereas in vestigial sideband, we only transmit the upper sideband with a portion of the lower sideband. So that's why it's called a vestigial sideband. And or we can say that we transmit the lower sideband, complete lower sideband, and the portion of the uh, upper sideband. So that's why it's called, due to vestige a portion, we call it as a vestigial sideband. And its bandwidth is around 25% greater than the single sideband. For example, if uh, SSB take one band 1 hertz, then it will take around 25% more than that of the SSB bandwidth. So it is not much bandwidth efficient as compared with SSB, but it's more a practical scheme. So baseband signal can be recovered by synchronous detection in conjunction with the output filter at the receiver. So it can be recovered similarly as we perform the synchronous detection by applying the uh, extra carrier at the receiver side. So we can similarly detect the vestigial sideband, but there is an additional output filter H0 F at the receiver. We will cover this content, how it works, and what is the transfer function of this receiver. We will cover in the later slides. So if larger carrier is transmitted, it means that if we transmit the additional carrier information beside the VSB modulated signal, then it can also be recovered by invariable detection. You know, the invariable detection, we don't need to uh, regenerate the carrier at the receiver side. So in the similarly in VSB, we can use the invariable detection if we transmit the additional carrier at the transmitter side. So to produce the single sideband signal from double sideband signal, ideal filter should be used to split the spectrum in the middle so that the bandwidth of a bandpass signal is reduced by 1/2. So we also need that one to produce single sideband. We need additional filter at the uh, transmitter side as well, which we called here in HIF, that is the input filter. So the transfer function of the input filter is HIF. In VSB system, one sideband and one vestige of the other sideband are transmitted together. As I mentioned, okay, let's plot as well. If this is the case of a double sideband, like for example, this is your upper sideband and this is the lower sideband, right? And for example, I am just plotting the positive side only. Okay, so this is the case when we have a single sideband modulation, right? There is a no other band. So this is the single sideband case SSB, and this we called as a DSB. And in vestigial sideband we have both of them. For example, this is the half single sideband and the portion will be here of a upper sideband as well. So with reference to this one. So this is called a vestigial sideband modulation. So they are mentioning that in one side VSB one sideband in this one and one vestige is transmitted, right, together. The resulting signal has a bandwidth greater than, of course, greater than the bandwidth of the modulating signal, but less than the double sideband signal bandwidth. For example, you need to transmit a modulating signal, so it will, of course, will be greater because we have a vestige here as well. So, but less than the double sideband signal bandwidth. So this is the double sideband signal bandwidth, and this is bit less than the this bandwidth, right? If this is B, so this can be B prime, right? This will be much less than the double sideband. We will see in the later slides how we can calculate the B dash. Okay, let's see. This is a comparison between the double sideband and double sideband, single sideband, and vestigial sideband. So how their spectrum looks like. So this is the double sideband case. They are plotting the both positive and negative as well. So let's only discuss this portion because this one will be similar to that one, right? So in double sideband, there is one upper sideband and the other lower sideband. In single sideband, this lower sideband is suppressed, right? It's plotted dotted to show that it is not transmitted. So only upper sideband is transmitted. Whereas you can see that in VSB spectrum, you have a upper sideband and the a vestige, a portion of the lower sideband as well. But we need to design, we need a filter which can accurately uh, cover this, accurately plot this shape, or we have a accurately, which we allow the accurate frequencies within this range. So this was a brief comparison between these three sidebands, three modulations. Okay, so this is a block diagram which shows how can we generate a VSB modulated signal out of the double sideband suppressed carrier modulated signal. So the other process is similar as double sideband modulation. Let's see. This is your message signal which you want to modulate. This is the product modulator. So product modulator will do, this is your carrier. So that will multiply these two, empty and the carrier signal, right? And in the end you will get the empty cos omega or cos 2 pi of ct, right, which is called double sideband suppressed carrier modulated wave. Why it's suppressed carrier? Because we are not additionally transmitted additional carrier beside the modulated signal. So what is the difference between VSB generation and the double sideband suppressed carrier generation? Up to this part it is similar, right? It is a double sideband suppressed carrier signal. But we need an additional band pass filter at the input which is called HIF here, right? So we need to pass the double sideband modulated signal with this filter in the, and then we will get the VSB modulated signal, right? So this is the only difference. So how this transfer function looks like, let's see. So if the input of the vestigial shaping filter is adapted to produce the VSB from the DSB, then the VSB transfer function should look like this one. This is similar as the double sideband modulated signal. The only difference is the half, so we ignore that one because we consider that at the input we are multiplying by 2, right, to balance out this. So this is a double sideband modulated signal, right? This is double sideband. So additionally we have a HIF term. This is the input filter. So we need to pass this double sideband modulated signal into the input filter. So this is the only difference between the DSB generation and the VSB generation. You must remember that one. Okay, these are the two block diagrams. One is for the transmitter, we already seen in the last slide, and this one is for the receiver side. Right after receiving the VSB, how we can get the message signal, right? Okay, this is a transmitter side. We already discussed 5 VSBF, MF minus FC, MF plus FC, right, into the HIF input filter. This is your input filter transfer function, this one, right? So we get 5 VSB-F. Now move to the receiver side. At the receiver side, to detect it synchronously, we need an additional carrier. This is cos omega ct. But we have a 2 here to balance the term at the receiver side. This is just for balancing. We already discussed in detail in double sideband modulation. So this 5 VSB, we are passing the 2 cos omega ct. We are passing to the product modulator. So we just again multiply this one. So we get at output E of t, right? So how it looks like? Let's see here. This is E of t 2 5 VSB cos omega ct, right? 2, I move the 2 from here to here, right? So 5 VSB cos omega ct. So you know that using the transmitter side equation 1, let's name it as equation 1. 5 VSBF looks like MF minus FC, MF plus FC, HIF. So let's put this into this value, right? So it becomes, because this one is the 5 VSB, so it becomes 5 VSB F plus FC and 5 F minus FC. Why? Because of multiplying with additional carrier here, we will get, after putting this one, right, and then multiplying with additional carrier, we will get this term 5 VSB F plus FC plus 5 VSB F minus FC and additionally HIF. Here it was a typo, right? HIF as well, right? You understand that one? Here there will be a bracket as well. So 5 VSB F plus FC, 5 VSB F minus FC, right? This one will be our received signal here, E of t. This is in time domain, but in frequency domain it will look like S, right? So 5 VSB F plus FC, 5 plus F minus FC into HIF, right? Let's move on, because now we need to know, generate this H naught F. This is the output filter. After passing this, we will get the message signal. So how this H naught F looks like and what should be the transfer function, let's calculate in the next slide. So after passing through the equalizer filter H naught F is called the equalizer filter because it will equalize and we will extract the original message out of the 5 VSB signal. So we have M of F, 5 VSB F plus FC, 5 VSB F minus FC into H naught F, right? So this is the, after passing this signal to the H naught F, the signal will look like this one, right? But we need to calculate what is the value, exact value of 5 VSB F plus FC and the 5 VSB F minus FC. So to calculate this, we will use our previous equation, 5 VSB F. We know it is F MF minus FC, and for example, where 5 VSBF is equal to MF plus FC, MF minus FC, HIF. So let's use this. So instead of only F here, we have additional term of FC. So put here F plus FC. So F plus FC plus FC, F minus FC plus FC, right, into HIF plus FC. Similarly, uh, which implies that 5 VSB F plus FC, this 2 FC will be added together, so it will be MF plus 2FC, and this 2 will be cancelled out because of different sign. So MF into HIF plus FC. Now we need to calculate the second term, F minus FC. Let's move on. So 5F VSB F minus FC. Similarly, we need to put F plus FC minus FC, F minus FC minus FC, and HI F minus FC. So that two terms will be cancelled out due to opposite side, and we will have a 2FC here minus 2FC here, right? And this will be MF only, right? This one. This is minus 2FC. And then as we are passing through the low pass filter, so we will ignore the high frequency term, like for example M. Now put these values 5 VSB F minus FC, and on the previous slide we calculated 5 F VSB F plus FC in the MF term. So after putting this, we will get equation something like that. You can just do the simple calculation, and because of passing through the low pass filter, as our term is targeted term is MF only, you know that the message is low frequency, so we ignore the high frequency term, so we cancel this one. In this way we can say that it is cancelled out. So what we left, MF equals to MF HIF plus FC, like this one, and HIF minus FC into H naught F, right? So uh, as we are targeting F should be less or equal to B, our bandwidth, it should not be greater, so these two will be cancelled out, and we will get, our target is to find H naught F, which would be equals to the 1 over HIF plus FC, HIF minus FC. It means that what we get, what it proves that the output filter is the function of the transfer function of the input filter, but the shifted version of the input filter, like HIF plus FC plus HIF minus FC. So we can calculate, if we have an input shaping filter, we can use that transfer function to calculate the output transfer function. So by using this transfer function, we can get the demodulated signal. So in this slide, we will discuss what is the exact value of the bandwidth consumed by the VSB. In double sideband, you know that we have a this type of this bandwidth, so it is around 2B, right? Is 2B, double of the modulated signal, and in single sideband we have a B bandwidth. However, in VSB we have an additional portion of this one, right? So bandwidth will extend from here, right, from here to there, right, this portion. So this is our bandwidth B. So how to calculate? So let's see. This is B, your center point, which is usually FC. So FC, and this is your message bandwidth, right? So FC, this is FC center point, and this portion is FC plus FM, right? FC plus FM, and that portion is we named it as a FV, because this is not a complete up to this one. Up to this one is FC minus FM, but we have a vestige, so FC we named it as a FC minus FV, that is the vestigial band, right? So the range is from FC plus FM to the FC minus FM. So what is the bandwidth? FC plus FM minus the difference, FC minus FV. So this is FV, this is FC. So let's open this. So minus FC, so FC will cancel out. So we have a bandwidth FM plus FV. So this is the bandwidth consumed by the vestigial sideband modulated signal. And there is some comparison between the modulated schemes which we covered in this course or in this chapter, because this one was the last scheme. So this, how their modulated signal looks like. This is AM signal. We have a additional carrier here as well. So AC1 plus MT cos 2 pi FCT. In double sideband, we have ACMT cos 2 pi FCT. Here we don't have a carrier, additional carrier, so it is called a double sideband AM with suppressed carrier, and it is with carrier AM, right? And this is the QM modulation. What is the difference? We have a quadrature phases, right? Cos and the sine. And in single sideband, we have a AC MT cos 2 pi FCT, AC M hat T sin 2 pi FCT. So this is the time domain function to represent the single sideband modulated signal. And in vestigial sideband, we have a similar like a function, but instead of M hat here, we have a M tilde to differentiate between them. So these are some message signals. The difference between them is clearly noticeable. And the bandwidth consumed is between the range of bandwidth message to the 2B. We have noticed that for other bandwidths in double sideband we have a 2B, For single sideband we have a BM, and for vestigial sideband which is in between DM and the 2DM. So this is the range of the vestigial sideband modulation or the overall bandwidth modulation system. Thank you for listening there. And for question answer section, there will be a separate slot. If you have any questions, then please prepare, and the exact date and time will be communicated to you later on. So please prepare yourself. Thank you for listening.